Imagine pointing the most powerful space telescope ever built at a patch of darkness so small it could hide behind a grain of sand held at arm's length. Nothing in that patch looks dramatic at first. No giant spiral fills the view. No nearby star burns white in the center. There are only faint dots, stretched smears, red sparks, and tiny fragments of light that look almost too weak to matter. But one of those faint red points is not just another galaxy. It is a message from a time when the universe was still almost newborn. Its light began traveling toward us, when space had not yet finished becoming transparent, when the first great cities of stars were only beginning to switch on, and when cosmic history should have still looked unfinished. That is why JADES-GS feels so strange. It is not frightening because it is a monster in the ordinary sense. It is frightening because it appears in a chapter where galaxies were supposed to be small, simple, dim, and young. Instead, it looks like the universe was already building faster than our timeline expected. Before we begin, subscribe to the channel for more calm journeys through the universe. Leave a like if you enjoy these deep space documentaries, and write in the comments where you are watching from and what time it is right now where you live. Tonight, you are watching the Just About Space channel, talking about JADES-GS breaks our timeline. And to understand why one faint galaxy can make astronomers rethink the early universe, we have to begin with the strange way telescopes turn distance into time. When we look across space, we do not see things as they are right now. We see them as they were when their light left. The moon is a little more than 1 light second away, so the moon in the sky is already a tiny moment old. The sun is about 8 light minutes away, so sunlight carries an 8-minute-old version of the star to our eyes. The nearest large galaxy, Andromeda, is seen as it was more than 2 million years ago. This is not a poetic idea. It is the basic price of light having a speed. Every telescope is also a time machine, but not because it changes time. It only waits for light that has already been traveling. The farther we look, the older the image becomes. A galaxy 10 billion light-years away is not just far. It is a preserved scene from 10 billion years in the past, stretched and reddened by the expansion of space itself. That means the deepest images from the James Webb Space Telescope are not just maps. They are archaeological layers. Nearer galaxies show a more recent universe. Fainter, redder points show earlier epochs. Somewhere in those red points is the boundary between a universe full of mature galaxies and a universe still trying to build its first real structures. JADES-GS belongs near that boundary. It is part of the JWST Advanced Deep Extragalactic Survey, a program designed to stare into early cosmic history and pull out signals that older telescopes could barely reach. The strange thing is not only that Webb found early galaxies. The strange thing is how bright, structured, and chemically interesting some of them appear to be. The name JADES, GS, Z14, 0 sounds almost deliberately unfriendly. It is not a name made for the public. It is a catalog label, the kind of label astronomers use when the sky contains too many discoveries for romantic names. JADES refers to the survey. GS points to the Goods South Field, a deeply studied region of sky in the constellation Fornax. The Z14 part points toward its redshift, the measure of how much the universe has stretched its light. And the 0 at the end marks one source among others. But hidden inside that technical name is one of the most extreme dates ever measured. JWST observations placed JADES, GS, Z14, 0 at a redshift around 14, meaning its light has been stretched so dramatically that wavelengths once emitted in the ultraviolet and visible range now arrive in infrared light. That matters because infrared is exactly the kind of light Webb was built to see. Older telescopes, especially those built mainly for visible light, could see far. Webb could see farther into the red, where the most ancient signals have been moved by cosmic expansion. Without that infrared vision, a galaxy like this does not announce itself as a beautiful spiral. It hides as a dim, red point. The universe has aged its light, stretched it, diluted it, and carried it across nearly all of cosmic history. By the time it reaches a mirror near Earth, the signal is so weak that the discovery depends on patience, cold instruments, careful spectra, and the ability to separate a true ancient galaxy from a nearby imposter that only looks red. That is why the redshift matters. A red galaxy in a telescope image is not automatically ancient. It might be dusty. It might be a closer object whose light has been reddened by material inside it. It might be a brown dwarf star in our own galaxy. It might be a faint source blended with another object. Early universe claims can rise quickly and fall just as quickly if the spectrum does not confirm them. For JADES, GS Z140, the critical step was spectroscopy. Instead of only taking a picture, Webb split the light into its components. Astronomers looked for the sharp signature left when neutral hydrogen absorbs light below a certain wavelength, the Lyman break. At very high redshift, that break moves far into the infrared. Finding it in the right place is like finding a cosmic barcode. It tells astronomers how much the light has stretched, which tells them how far back they are looking. That is why the object became so important. It was not simply a red smudge that someone guessed might be old. It had a measured redshift supported by Webb's instruments. And once that redshift was accepted, the timeline became uncomfortable. The light was showing a galaxy from less than 300 million years after the Big Bang, a time when the universe was only a small fraction of its current age. 300 million years may sound enormous beside a human lifetime. In cosmic history, it is early morning. To feel why that is strange, imagine compressing the entire age of the universe into one calendar year. The Big Bang happens at midnight on January 1st. The present moment lands at the final seconds of December 31st. In that scale, JADES GS Z140 appears in the first week of January. It is not a late galaxy looking back at its childhood. It is a galaxy found near the opening pages, before the universe has had much time to gather gas, make stars, explode those stars, enrich the gas with heavier elements, and build larger structures. The usual story begins with darkness. After the hot early universe cooled, atoms formed, light was released, and then space entered a long period before the first stars fully transformed it. Gravity slowly pulled tiny density differences into larger clumps. Dark matter gathered first, creating invisible wells. Gas fell into those wells, cooled, condensed, and eventually ignited as the first stars. Those stars were expected to be massive, short-lived, and violent. They made the first heavy elements and changed the chemistry of the universe. Galaxies were supposed to assemble gradually from this beginning. They did not need to be absent at 300 million years, but many models expected the earliest bright ones to be rare, small, and difficult to explain. Then Webb began finding more luminous early objects than many astronomers had prepared for. JADES GS Z140 became one of the cleanest examples of that surprise. The word timeline can be misleading because discoveries like this do not mean the Big Bang model is broken in the simple internet sense. They do not mean the universe is secretly older than physics says, or that everything scientists know has collapsed overnight. The deeper issue is more specific and more interesting. A timeline is not only the age of the universe, it is also the expected pace of structure formation. How fast can dark matter halos grow? How efficiently can gas cool? How quickly can the first stars form? How rapidly can heavy elements appear? How bright can a young galaxy become before its own radiation and supernovae push gas away? These are not small details. They decide what the first hundreds of millions of years should look like. If a galaxy is already bright and chemically active very early, then something in the recipe may need adjusting. Maybe star formation was more efficient than expected. Maybe the first galaxies were burstier. Maybe dust, feedback, or massive stars behaved differently in the early universe. Maybe the dark matter halos that hosted these systems grew faster in rare, dense regions. The frightening part is not that the universe disobeyed reality. The frightening part is that reality may have always been more productive, more violent, and more advanced at the beginning than our mental picture allowed. The universe before JADES-GS was not empty. It was filled with material, but not material arranged in the familiar way. There were no old spiral galaxies like the Milky Way with calm arms and long histories. There were no planets like Earth yet, because rocky worlds need elements forged in earlier stars. There were no ancient globular clusters orbiting mature galaxies. There was mostly hydrogen and helium, with traces of lithium expanding through space and falling into the first gravitational wells. Dark matter shaped much of that process. Because dark matter does not shine, it does not cool and collapse the way normal gas does, but its gravity creates the scaffolding. Gas collects inside those invisible halos. If enough gas gathers, it can cool, fragment, and form stars. The first stars may have been very different from stars today, because the gas lacked heavier elements that help it cool into smaller pieces. Large stars burn fast, explode quickly, and seed their surroundings. So the earliest galaxies were not calm nurseries. They were unstable engines. Gas rushed in. Stars formed in bursts. Radiation blasted outward. Supernovae shook the young system. Fresh elements mixed with raw hydrogen. If JADES-GS Z14 already shows signs of strong star formation and later chemical enrichment, then it is a clue that this engine may have been running at a frightening speed. One reason JADES-GS Z140 caught attention is that it was not only far away, it was bright. In the early universe, brightness is a difficult thing. To shine strongly in ultraviolet light, a young galaxy needs many hot, massive stars. Those stars do not live long, which means the galaxy must be actively forming them or must have formed them recently. A faint, young galaxy would be easier to understand. It could be one of countless small seeds, starting slowly in the dark. A surprisingly luminous one demands more. It asks for enough gas, enough gravity, enough efficiency, and enough time for a large population of stars to appear. It also asks why the light escaped. Early galaxies were surrounded by gas. The universe itself still contained neutral hydrogen in many places, which could absorb or scatter ultraviolet light. Dust can hide stars too, if dust has already formed. So a bright object near cosmic dawn is not just a lamp. It is a lamp that somehow built itself quickly and allowed some of its light to escape across the young universe. That is why the discovery does not feel like a distant trivia fact. It becomes a test. The first question is not simply how far away it is. The first question is what had to happen before that light could exist. The phrase, cosmic dawn, sounds peaceful, but it was not a calm sunrise. It was the era when the first stars and galaxies began changing everything. Before that, the universe had cooled enough for atoms to form, but much of space remained dark to ordinary eyes. Gravity worked quietly for tens and hundreds of millions of years, pulling matter into clumps. Then, stars ignited. Their radiation began carving bubbles through surrounding hydrogen. Their explosions threw heavier elements into space. Their heat and light started transforming the intergalactic medium. This process eventually led to reionization, when much of the neutral hydrogen between galaxies became ionized again. But reionization was not a single switch flipped everywhere at once. It was patchy, uneven, and messy. Some regions may have lit up earlier. Some galaxies may have formed in unusually dense neighborhoods. Some sources may have cleared tunnels through gas, allowing radiation to escape. A galaxy like JADES, GS Z14 appears in this complicated borderland. It belongs to a time when the universe was still foggy in a cosmic sense, but already capable of producing lights bright enough for Webb to see today. That combination is the reason it feels like a timeline problem. It is not showing an impossible universe. It is showing a universe that got busy extremely fast. There is another layer that makes it even stranger: oxygen. Hydrogen and helium came from the early universe itself. Oxygen did not. Oxygen is made inside stars and spread by stellar deaths. To detect oxygen in a galaxy seen so early is to find evidence that some stars had already been born, lived, died, and enriched the gas before the moment we are observing. That compresses the schedule. First, gas had to collect. Then, stars had to ignite. Then massive stars had to burn through their short lives. Then, they had to release heavier elements. Then those elements had to mix into the galaxy. Then the galaxy still had to remain bright enough for us to detect its light billions of years later. None of those steps is impossible in principle, because massive stars can live only a few million years. But seeing chemical maturity so early forces astronomers to think carefully about how intense the first star formation episodes were. It also gives the galaxy a different emotional weight. We are not looking at untouched cosmic material. We are looking at a place where the first cycle of creation and destruction had already happened. In a universe that had barely begun, something had already built stars, destroyed them, and carried their ashes into new gas. This is where the title becomes more than a hook. JADES-GS breaks our timeline because it turns the first few 100 million years from a slow warm-up into a crowded sequence of events. The universe did not simply cool, wait, and then gradually become interesting. In some regions, it appears to have assembled luminous structures almost immediately by cosmic standards. A useful way to picture this is not as a single giant galaxy forming fully mature from nothing. It is better to imagine a young, compact, active system in a rare, overdense patch, where gas streams in quickly and star formation becomes intense. The galaxy does not need to look like the Milky Way. It can be irregular, clumpy, and unstable. It can be small by modern galactic standards and still be shocking for its time. The timeline problem is that even a small galaxy can be too bright, too active, or too chemically developed for a simple early universe picture. It is like finding a city with lights on during an age when you expected only campfires. The existence of the city does not mean civilization is impossible. It means your estimate of how fast construction began was too slow. The James Webb Space Telescope was designed for precisely this kind of discomfort. Hubble gave humanity some of the deepest optical views ever taken, but the earliest galaxies are shifted so far into infrared light that Webb had to take over. Webb's large segmented mirror collects faint light. Its instruments sit cold enough to detect infrared signals without drowning in their own heat. Its cameras and spectrographs can separate candidates by color, then confirm them through spectra. In the JADES program, astronomers used deep imaging to identify possible high redshift galaxies. Then they used NIR-SPEC, Webb's near-infrared spectrograph, to study selected objects in more detail. This matters because astronomy at the edge of the observable universe is not one dramatic photograph. It is a chain of evidence. A source appears in some filters and disappears in others. Its colors suggest a sharp break. Its light is split into a spectrum. The position of that break gives the redshift. Other measurements test whether it could be a closer object. When enough pieces agree, the little red point becomes a timestamp. JADES-GS Z140 is one of those timestamps. It tells us there was already a real luminous galaxy less than 300 million years after the beginning we can trace. But even the phrase less than 300 million years after the Big Bang needs careful handling. The Big Bang was not an explosion into empty space from a single point. It was the early, hot, dense state from which the observable universe expanded. When we say a galaxy existed 300 million years after the Big Bang, we mean its light left when the universe itself was that young. Because the universe has expanded during the light's journey, its present distance is not simply the same as its light travel time. This is why distance in cosmology can sound confusing. The light can take more than 13 billion years to reach us, while the current separation, if defined by today's cosmic scale, can be much larger. The numbers are not contradictions. They are different ways of describing an expanding universe. For a script like this, the important point is simple. JADES-GS Z140 shows us a scene from almost the beginning of galaxy history. It is not near in any ordinary sense. It is not old in the way nearby ancient stars are old. It is ancient light from a young object. We see the galaxy as a baby universe saw it, not as it might be now. If it still exists in some evolved form, that version is forever beyond the image we receive. The galaxy also reminds us that looking far away is not like watching a movie from beginning to end. We do not get a continuous recording of one object growing across time. We get scattered frames from different objects at different distances. Nearby galaxies show later stages. Very distant galaxies show early stages. Astronomers then build a history by comparing populations, simulations, spectra, and physical models. JADES-GS is one frame from an early chapter, but it is a powerful frame because it forces the surrounding story to tighten. If a galaxy this bright exists at this age, then earlier steps had to happen before it. The first stars had to ignite even earlier. Their feedback had to shape the gas. The dark matter halo had to gather enough material. The environment had to support rapid assembly. In this way, JADES-GS Z140 points backward toward epochs we still cannot see clearly. It is not only a discovery, it is an arrow. It says, if this was already here, then something happened before this, faster than expected. The faint red dot becomes evidence for a hidden prehistory of the luminous universe. That hidden prehistory is one of the most important parts of the video. We often imagine the first galaxy as a single dramatic object, switching on in the dark. In reality, the first galaxies were likely a messy population. Some were tiny. Some merged quickly. Some flickered through bursts of star formation. Some may have been temporarily hidden by dust or gas. Some may have produced intense radiation and then faded. The universe was not waiting for one official first galaxy. It was growing structure across many regions at once. JADES-GS Z140 is visible because it happened to be luminous enough, distant enough, and positioned in a field Webb observed deeply. It is not necessarily the first galaxy. It is one of the earliest confirmed windows we have into a time when the first generation of galaxies was already active. That distinction keeps the science honest and makes the mystery stronger. The real question is not whether this single galaxy is the oldest thing in all existence. The real question is how many similar objects were already out there, too faint or too hidden for us to recognize yet. If JADES-GS is one bright clue, the early universe may have been full of smaller clues still waiting below our detection limits. The challenge is that early galaxies are almost impossibly hard to read. Their light is faint. Their signals are stretched. Their shapes are tiny. Their internal details are blurred by distance. A galaxy that may span more than 1,000 light-years appears as a small source in an infrared image. We cannot fly there, cannot watch it evolve, and cannot separate every star. We infer, we model, we compare. Even when the redshift is secure, other properties carry uncertainties. How massive is it? How much dust does it contain? How fast is it forming stars? What kind of stars dominate the light? Is there a hidden black hole helping power it? Or is the brightness mostly from young stars? These questions matter because the interpretation changes the timeline. If a hidden active black hole contributes strongly, the galaxy may not need as many stars to shine. If the light comes mainly from stars, then the star formation efficiency may be astonishing. If dust is present, it may hide part of the system and reveal a different history. If oxygen is present, there has already been enrichment. Each measurement narrows the possibilities, but no single image solves everything. That is what makes JADES-GS scientifically exciting. It is not a finished answer. It is a pressure point where different models must survive contact with data. One of the most useful comparisons is with the Milky Way, but it must be made carefully. The Milky Way is a vast spiral galaxy with hundreds of billions of stars, a long history of mergers and star formation, a central black hole, spiral arms, dust lanes, and a halo of older stars. JADES GS Z140 is not a baby Milky Way in the simple sense. It is an early galaxy seen when the universe was young. It may be compact, irregular, and dominated by young hot stars. Its environment, chemistry, and radiation field would be nothing like the calm night sky over Earth. But comparing it to modern galaxies helps us understand what had not yet happened. There had not been billions of years for stable disks to settle in the same way. There had not been time for many generations of stars to enrich the galaxy to modern levels. There had not been time for galaxy clusters and filaments to develop into the familiar structures we map today. So when an early galaxy appears already bright and complex, it is not because it resembles a finished modern galaxy. It is because the universe found a way to create an intense early system before the cosmic clock had moved very far. The word breaks is dramatic, and it should be used responsibly. JADES-GS does not break physics like glass. It breaks a comfortable expectation. The universe was not supposed to be empty at that time, but it was expected to be difficult for large, bright galaxies to appear so soon. After Webb, astronomers had to take seriously the possibility that galaxy formation at cosmic dawn was more efficient, more bursty, or more varied than earlier observations suggested. Some simulations already allowed rare bright objects. Others needed adjustment. Some apparent tensions may shrink as data improve because distance estimates, stellar population models, and selection effects matter. But the emotional power remains. We built a timeline from the best evidence we had. Then, a telescope looked deeper and found that the early chapters were not as quiet as they seemed. This is how science often changes, not by throwing out everything, but by making the details sharper. The galaxy becomes a correction written in infrared light. It tells us the universe was capable of speed, structure, and chemistry almost immediately by cosmic standards. That is more unsettling than a simple contradiction, because it means the hidden beginning was richer than the visible one. To understand how such a galaxy could appear, we have to follow the invisible architecture beneath it. Dark matter does not emit light, but it dominates the gravitational scaffolding of early structure. Tiny density fluctuations, visible indirectly in the cosmic microwave background, became seeds. Regions with slightly more matter pulled in more matter. Over time, these grew into dark matter halos. Gas followed the gravity, fell inward, heated, cooled, and sometimes formed stars. The most extreme early galaxies likely lived in rare peaks, regions where matter was unusually dense compared with the average. In those places, growth happened faster. More gas arrived. Mergers occurred earlier. Star formation could ignite violently. A galaxy like JADES-GS may therefore not represent the average young universe. It may represent one of the rare places where the universe ran ahead. But rare is not the same as impossible. If the observable universe is vast enough, rare events still happen somewhere. Webb's job is to find them, count them, and force models to predict their abundance. One unexpected galaxy can be interesting. A population of them becomes a revolution. This is why counting early galaxies matters almost as much as studying one of them. If JADES, GS, Z140 were alone, astronomers might treat it as an extreme outlier. But Webb has found many surprisingly early candidates and confirmed several very distant galaxies. Each one adds pressure. The number of bright galaxies at high redshift tells us about the first dark matter halos, the efficiency of star formation, the nature of feedback, and the transparency of the early universe. A single record breaker gives a headline. A statistical sample rewrites the story. The JADES survey is valuable because it does not only hunt trophies, it maps a deep field, builds a population, and connects objects to a broader picture of cosmic dawn. If early galaxies are more common or brighter than expected, we must ask why. Are stars forming in a top-heavy way, with more massive hot stars than usual? Are small galaxies converting gas into stars with unusual efficiency? Are we underestimating the role of bursts? Are black holes growing early and influencing their surroundings? These questions are not abstract. They decide how quickly the first light transformed the universe. A related mystery is dust. Dust sounds ordinary, but cosmic dust is made from heavier elements. It does not exist before stars create and distribute those elements. In young galaxies, dust can both reveal and hide history. It can dim ultraviolet light, redden a source, shield gas, help molecules form, and change how star formation appears to a telescope. If an early galaxy contains dust, then earlier stars have already enriched it. If it lacks much dust, its light may escape more easily, but the absence also tells us about its chemical state. Models of early galaxies must decide how quickly dust can form, survive supernova shocks, and spread through the interstellar medium. JADES, GS, Z140 sits in the middle of these questions, because its brightness and chemical clues suggest rapid development, while observations continue to test how much dust and gas are actually present. This keeps the story grounded. The timeline does not break because of one sensational number. It bends under many small measurements: light, redshift, size, oxygen, dust limits, star formation, and the physics of gas. Then there is the question of size. In ordinary imagination, the earliest galaxies should be tiny sparks somewhere, but a galaxy can be physically small and still shocking if it shines strongly enough. JADES, GS, Z140 has been described as extended rather than merely point-like, meaning Webb saw more than a simple unresolved dot. That matters, because if the light came from a tiny active nucleus alone, the interpretation would be different. An extended source suggests stars spread across a region, a real galaxy rather than only a central engine. This does not mean it was huge like modern spirals. It means it had already assembled a luminous stellar system of meaningful scale. At less than 300 million years after the Big Bang, even a few hundred or more light years of active structure is important. It tells us gravity had already gathered material into a working galaxy. It tells us gas had cooled and stars had formed across a region. It tells us cosmic dawn had architecture, not just isolated fires. The early universe, seen through Webb, is less like a blank stage and more like a construction site, already full of scaffolds, lights, engines, and unfinished buildings. The phrase oldest galaxy can also confuse people. JADES, GS Z14. 0 is not old in the picture. In the picture, it is young. Its light is old because it has traveled for almost the entire history of the universe. We are seeing a young galaxy through ancient light. That is one of the strange mental turns required by cosmology. The most distant galaxies are the youngest versions of galaxies we can observe. Nearby old galaxies may contain ancient stars, but their light reaches us from a recent time. Distant early galaxies show us the universe when those galaxies were still forming. So if someone says JADES-GS is one of the oldest galaxies known, they usually mean it is one of the earliest galaxies we have observed, not that the object looked elderly when the light left. The galaxy in the image is a newborn by cosmic standards. But it is a newborn that already seems unusually developed. That is the paradox at the center of the story. We expected youth, we found youth, but youth with signs of history already inside it. That paradox becomes sharper when we think about elements. The first stars formed from almost pure hydrogen and helium. Everything heavier, including oxygen, carbon, nitrogen, silicon, and iron, had to be created later. A galaxy rich in heavy elements requires earlier stellar generations. Oxygen, in particular, is produced by massive stars and released when they die. Massive stars can live fast, so enrichment can begin quickly, but quick does not mean automatic. The gas must form stars. Those stars must explode or shed material. The enriched material must mix. New regions must shine with emissions that instruments can detect. When ARMA detects oxygen in such a distant galaxy, it gives the early universe texture. It says that cosmic dawn was not chemically blank. It had already begun turning simple gas into the ingredients of later planets, atmospheres, and life. Of course, no one is saying JADES-GS had planets like Earth. It existed far too early for that familiar story. But the detection of oxygen means the first steps toward complexity were already underway. The universe was already making more than light. It was making the periodic table. The deeper fear in this topic is not personal danger. No one is threatened by JADES, GS, Z14, 0. It is too far away, too ancient in the form we see, and too unreachable. The fear is intellectual. It is the feeling that the universe does not care about our neat sequence of chapters. We want the beginning to move slowly enough for us to understand. First darkness, then a few stars, then tiny galaxies, then larger galaxies, then maturity. Webb shows that the order may still be broadly right, but the pace can be startling. Instead of a gentle dawn, there may have been a violent, efficient burst of structure in rare places. Instead of waiting patiently, matter may have collapsed, burned, exploded, and enriched itself with astonishing speed. The timeline becomes less like a straight staircase and more like a storm front. Some regions lagged behind. Some raced ahead. JADES-GS is terrifying because it reminds us that the early universe was not simple just because it was young. It may have been simple in ingredients, but not simple in behavior. This also changes how we imagine the first black holes. Early galaxies may have hosted black holes that grew quickly from massive stellar remnants, direct collapse seeds, or other pathways still being debated. Some early bright objects may be powered partly by accreting black holes. If a black hole is feeding, gas spirals inward, heats intensely, and can outshine stars in certain wavelengths. For JADES, GS, Z14, 0, the brightness is not automatically explained by a black hole, and much of the discussion centers on stellar light and galaxy properties. But the broader Webb era has made early black holes a major part of the puzzle. If black holes grew early, they could help regulate galaxies, drive outflows, heat gas, and affect star formation. If they did not dominate, then stars themselves were doing extraordinary work. Either way, the timeline becomes more active. The early universe was not only forming stars, it may have been building compact engines of gravity too. Some of those engines may have shaped their host galaxies long before the universe had reached even a few % of its current age. There is a quiet technical detail behind all of this. Selection. Telescopes do not see every galaxy equally. They are more likely to detect objects that are bright, exposed, and positioned in surveyed fields. A galaxy hidden by dust might be missed in one wavelength and found in another. A faint galaxy may fall below the limit. A small, bright burst may be easier to detect than a larger, dim system. So when Webb finds a bright early galaxy, astronomers must ask how representative it is. Are we seeing the visible tip of a much larger population, or a rare object that happens to stand out? Are there many hidden galaxies that do not show up in the same way? Are our surveys biased toward unusual systems? These questions prevent the story from becoming too simple. JADES-GS does not tell us everything by itself. It tells us where to look harder. It shows that the early universe can produce objects at the edge of our expectations. Then the next step is to map enough of them to know whether our expectations were merely incomplete or fundamentally too cautious. The first half of this journey, therefore, leads to a clear but unsettling conclusion. JADES-GS Z14. 0 is important not because it is a single dot with a dramatic label, but because it compresses cosmic history into an almost impossible schedule. It tells us that by the time the universe was less than 300 million years old, there were already galaxies bright enough for Webb to detect, active enough to produce strong light, and developed enough to carry chemical clues that point to earlier generations of stars. It forces us to ask how quickly the first stars formed, how rapidly gas collapsed into halos, how soon heavy elements spread, and whether the cosmic dawn was much more crowded than we imagined. The next part of the story has to go deeper into what this means for the first galaxies. As a population, why Webb keeps finding objects that look too early, and how future telescopes may either solve the timeline problem or make it even stranger. Because JADES-GS may not be the exception that breaks the story. It may be the first clear sign that the story of the early universe was always faster, brighter, and more complicated than the timeline we built before Webb could see it. Another way to understand the shock is to compare observation with expectation. Before Webb, many of the most distant galaxies were known through Hubble and ground-based surveys. But those instruments could only push so far. The earliest candidates were often tiny, faint, and uncertain. Webb widened the window, and suddenly the edge of the known universe looked less empty. That does not mean every early bright point is automatically real, because false candidates still happen. It means the confirmed examples carry more weight. JADES GS Z140 is part of that shift. It gives astronomers a confirmed point deep in cosmic dawn, not merely a suggestion. Once that point exists, simulations must explain it without using magic. They must create enough structure, enough stars, enough light, and enough chemistry by the same cosmic age. If they cannot, the models change. If they can, then we learn what physical conditions made the early universe so efficient. Both outcomes are valuable. The galaxy wins either way because it forces the question to become sharper. The strangest thing is how small the evidence looks compared with the size of the conclusion. A faint source in an infrared field becomes a clue about the first stars. A shifted break in a spectrum becomes a date near the beginning of galaxies. A line of oxygen becomes evidence for previous stellar deaths. A measurement of brightness becomes a challenge to star formation models. This is the quiet drama of astronomy. The universe does not hand us a written history. It gives us weak light, stretched wavelengths, and objects too far away to touch. From those fragments, scientists rebuild a timeline billions of years long. JADES, GS, Z14. Zero matters because the fragments do not fit the simplest version of that timeline. They suggest a universe that was already arranging matter into luminous systems at astonishing speed. That is why a small red galaxy can feel larger than its image. It carries the weight of everything that had to happen before it. There is also a psychological problem hidden inside early galaxy astronomy. We are used to thinking of beginnings as clean. A beginning should be simple, empty, and slow. It should give us time to watch complexity arrive one step at a time. But the universe may not respect that instinct. The first few 100 million years were not a quiet introduction designed for human understanding. They were a physical environment where gravity had already been working everywhere, where dark matter had already organized material into a vast network, and where gas could fall into the deepest early wells with violent speed. If the first stars were massive, their lives were short. If their lives were short, their deaths came quickly. If their deaths came quickly, the chemistry of the next generation changed almost immediately. This means the beginning could be both young and busy at the same time. JADES, GS, Z140 becomes a symbol of that contradiction. It is young enough to belong near the first light, yet busy enough to suggest earlier episodes of formation, feedback, and enrichment. It makes cosmic dawn feel less like a sunrise and more like an explosion of construction seen through fog. The fog is important because the early universe was not fully transparent in the way nearby space is transparent. Neutral hydrogen between galaxies could absorb certain ultraviolet photons. Light from early stars and galaxies had to carve its way through that material. Over time, bubbles of ionized gas grew around luminous sources. Those bubbles expanded, overlapped, and helped end the cosmic dark ages. A bright early galaxy is not only a passive object in that process. It may be an actor. Its young massive stars could release energetic radiation. If enough of that radiation escaped, it could help ionize nearby gas. This is one reason astronomers care about galaxies at redshift 14 and beyond. They are not merely distant trophies. They may be part of the machinery that transformed the universe from opaque and neutral into something closer to the space we observe today. JADES, GS, Z140 sits so early that it raises a sharp question. Were galaxies like this already helping clear the fog, or were they still trapped inside it? The answer changes how we understand reionization, one of the great turning points in cosmic history. To make the problem more concrete, imagine trying to build the galaxy from raw ingredients. Start with a small enhancement in dark matter density. Let it grow as the universe expands. Allow gas to fall inward. The gas heats as it collapses, then must cool enough to fragment. Without heavy elements, cooling is harder, so the earliest stars may form in large masses. Those stars ignite, blast radiation outward, and push against the very gas the galaxy needs for continued growth. Some explode. Their shockwaves can compress nearby gas or throw it away. Metals spread unevenly. New stars form from material that is no longer pristine. The galaxy flickers between building and disrupting itself. If the system is too weak, feedback shuts it down. If it is deep enough, it keeps pulling gas back. JADES, GS, Z140 implies that in at least one place, the balance worked quickly. Gravity, cooling, star formation, feedback, and enrichment all produced a detectable system before the universe had reached 300 million years. That is not a minor scheduling issue. It is an entire physics pipeline running at extreme speed. The James Webb images can make this feel deceptively simple. On screen, the galaxy is a dot. A tiny point does not look like a storm of gas and young stars. It does not show the violence of stellar birth or the shock of supernovae. It does not show dark matter flowing invisibly around it. It does not show the intergalactic gas outside it, absorbing and scattering light. A deep field image compresses everything into stillness. But stillness is a trick caused by distance. The object was not still. It was forming, heating, shining, and changing. Its stars were burning through fuel. Its gas was responding to gravity and radiation. Its light was beginning a journey that would outlast species, continents, and planets. By the time the photons reached the telescope, the galaxy's original environment had long since evolved into something else. The image is quiet because the light is old, not because the event was calm. That is why these discoveries work so well for a calm documentary. The visuals can be soft and dark, but the physics underneath is fast and intense. Another question is whether JADES-GS Z140 is telling us about the ordinary universe or about a rare cosmic neighborhood. The early universe was not perfectly smooth. Tiny differences in density mattered. A region slightly denser than average could collapse earlier. A rare peak could produce large halos before most of space had caught up. If a telescope happens to find one of those rare peaks, the result may look surprising without representing every region. But rarity itself becomes meaningful. If surveys find one rare object in a small patch, astronomers can estimate how common such objects might be across the whole sky. If too many appear, the models must explain why rare peaks are not as rare as expected, or why the galaxies inside them are brighter than predicted. This is where JADES becomes a statistical tool rather than a single story. It is part of a survey designed to measure early galaxies in a controlled way. The more confirmed objects appear at extreme redshift, the more the early universe begins to look crowded with activity. A crowded cosmic dawn is much harder to fit into old instincts about slow beginnings. There is also a difference between breaking the timeline and breaking the age of the universe. Some online discussions jump from early galaxies to the claim that the universe must be older than we think. That is not the careful conclusion. The age of the universe comes from many lines of evidence, including the cosmic microwave background, expansion measurements, and the physics of the early plasma. A surprising galaxy does not erase that foundation. Instead, it challenges the astrophysics of galaxy formation inside that age. It asks how matter behaved within the time available. The distinction matters because the real mystery is more subtle. It is not that the clock is necessarily wrong. It is that the universe may have done more work before the clock reached 300 million years than many models anticipated. That is a much better story for a documentary because it avoids false drama and keeps the true drama. The universe did not need more time to become strange. It may have used the time it had more efficiently than we thought. The idea of efficiency can sound dry, but in early galaxies it is everything. Star formation efficiency describes how much available gas turns into stars. In modern galaxies, star formation is regulated by turbulence, magnetic fields, radiation, stellar winds, supernovae, and the supply of gas. The Milky Way is not turning all of its gas into stars at once. It forms stars gradually in clouds. At cosmic dawn, conditions were different. Gas fractions were higher. Dark matter halos were younger. Mergers were more common. Radiation fields were harsher. If early galaxies converted gas into stars with unusually high efficiency, they could become bright sooner. If star formation happened in short bursts, a galaxy could appear very luminous during a temporary phase. If the first stars were more massive, their ultraviolet output could be intense. JADES JWST forces these possibilities onto the table. Its brightness is not only a number, it is a demand placed on the machinery of star formation. Something had to make that light, and it had to make it early. One of the most important lessons from Webb is that the universe may be more varied at early times than older images suggested. Before Webb, much of cosmic dawn was hidden behind technological limits. A small sample can make nature look simpler than it is. When a better instrument arrives, the sample changes. Suddenly, astronomers see objects that were always there but not accessible. This is not a failure of earlier science. It is how exploration works. A coastline looks smooth from far away. Up close, it becomes cliffs, caves, islands, and channels. The early universe may be similar. Hubble showed the outline. Webb shows more texture. JADES-GS Z14 is one of the sharpest pieces of that texture. It tells us that the first chapters were not a blank gradient from darkness to light. They had exceptions, bursts, rare peaks, and chemically interesting systems. Every one of those details helps turn a simple story into a real one. The galaxy's discovery also changes the emotional scale of deep time. Human history is measured in thousands of years. Civilization is recent. Life on Earth spans billions of years, but even that is local. JADES-GS Z14 pushes us into a time when Earth did not exist, the Sun did not exist, and the Milky Way itself was still assembling. Yet the physical processes that would eventually make planets and people were already underway elsewhere. Stars were forming. Elements were being made. Gravity was building structure. Light was beginning journeys that would one day be caught by machines built on a planet that had not yet been born. That connection is almost impossible to hold in the mind. The photons from JADES-GS traveled across the universe while generations of galaxies formed, while our solar system condensed, while life emerged, and while intelligence eventually built Webb to receive them. The galaxy does not only break a scientific timeline, it collapses the distance between cosmic origin and human curiosity. This is why the first half of the script should not treat JADES-GS as a simple record. Records are temporary. A newer survey can find a more distant object. A candidate can be confirmed beyond it. Names at the edge of the universe will change as telescopes improve. What matters more is the lesson. JADES-GS Z14 showed that the early universe was already capable of producing a bright, distant, chemically revealing galaxy extremely soon after the Big Bang. Even if another galaxy eventually takes the record, this one remains important because it helped change the question. Instead of asking whether Webb could see the first galaxies, astronomers began asking why the first galaxies were so bright, how they formed so quickly, and how many more are hiding at even earlier times. That is the correct way to frame the mystery. The point is not to worship a catalog name. The point is to follow the crack it opened in our understanding. By the end of this first half, the viewer should feel the shape of the problem clearly. A telescope looked into a deep field. A red source appeared. Spectroscopy placed it near redshift 14. That means we are seeing it from a time when the universe was less than 300 million years old. The source was not just present. It was luminous. It showed signs that connect to star formation, gas, and chemical evolution. That forces a chain of earlier events. Dark matter halos forming, gas collapsing, stars igniting, massive stars dying, heavy elements spreading, and light escaping. Every link in that chain had to fit into a narrow cosmic window. That is the timeline pressure. The next half of the story can then ask, what happens if JADES-GS is not alone? How future telescopes may push closer to the first stars? and why the youngest galaxies may reveal a universe that built complexity before we thought it had time to do so. For now, the most important idea is simple. The beginning was not empty for long, and perhaps that is the most unsettling part of all. We often treat cosmic history as if the universe waited patiently for the later chapters to become interesting. But JADES-GS suggests that the early chapters already contained speed, violence, chemistry, and surprise. The first galaxies were not decorative lights placed on a finished stage. They were engines that changed the stage itself. They heated gas, enriched space, carved ionized bubbles, and began the long process that eventually led to mature galaxies like our own. When Webb finds one of them so early, it does not simply extend a record. It tells us the universe became creative almost immediately. It tells us that the line between darkness and structure may have been crossed sooner, faster, and in more places than expected. And it leaves us with a question that cannot be answered by one image. If this much had already happened by then, what happened before the first light Webb can clearly show us? To answer that, we have to move farther back than the galaxy itself, into the darker time when its ingredients were still being prepared. Before JADES-GS Z14 could shine, before its stars could pour ultraviolet light into space, before oxygen could appear in its gas, there had to be a chain of events hidden behind the object we now detect. The telescope does not show that chain directly. It gives us a late clue from an early time. It shows the result of processes that must have started even earlier. That is why the galaxy feels so uncomfortable. It is not only a distant object. It is evidence of an unseen beginning behind an already ancient beginning. The first hidden step is dark matter. Long before the first visible galaxies, the universe contained small differences in density. They were not large structures yet. They were slight, uneven places in an expanding sea. Ordinary matter, the gas that would one day make stars, was still hot and tied to radiation during the earliest phase. Dark matter did not interact with light in the same way. It could begin forming the invisible scaffolding before ordinary atoms were ready to collapse efficiently. Those early dark matter concentrations were not galaxies. They were potential wells, gravitational traps, places where gas would later collect. If JADES-GS Z14 was already bright, less than 300 million years after the Big Bang, then the dark matter halo behind it had to begin assembling quickly. It needed enough gravity to hold gas, resist being emptied by young stars, and survive the violence of its own formation. That is the first timeline pressure. A galaxy is not built from light. Light is the final visible symptom. The real construction starts in darkness. The halo must form inward. The gas must lose heat. It must collapse into dense regions. Stars must form. Massive stars must die. Their material must mix. New stars must continue forming. And enough light must escape for Webb to see it across almost the entire history of the universe. When we say JADES-GS breaks our timeline, this is the timeline we mean. Not a calendar printed in a textbook, but a sequence of physical steps, each one demanding time, mass, and the right conditions. The first stars add another layer. Astronomers often call them population 3 stars, although none has been directly observed yet. They are expected to have formed from nearly pristine hydrogen and helium, with almost no heavier elements. Without carbon, oxygen, silicon, or iron, early gas cooled differently. That changes the masses of the first stars. Many models suggest that some of the first stars may have been enormous, far more massive than the Sun, burning fiercely and dying quickly. If those stars existed in or near the ancestry of JADES-GS JWST, they could help explain how chemical enrichment started so early. A massive star can live fast. It can shine for only a few million years, collapse, explode, and seed its surroundings with newly formed elements. On human time, that is almost eternity. On cosmic time, it is a spark. This matters because oxygen is not primordial. The Big Bang made mostly hydrogen and helium with a trace of light elements. Oxygen has to be forged inside stars. It has to be released by stellar death or powerful stellar winds. It has to enter the gas around later generations of stars. So when ALMA finds oxygen associated with a galaxy from such an early era, the discovery carries a buried history. It is not just a chemical line. It is a fossil of earlier stars. It says that at least some stellar birth and death had already happened before the moment we are observing. The galaxy was not merely beginning. It had already processed material. It had already changed itself. That is what makes the story feel almost too fast. If the universe was less than 300 million years old, at the time we see JADES-GS Z140, then the first stars in its ancestry may have needed to form much earlier. They needed time to ignite, evolve, explode, and enrich the environment. Then the next wave of star formation had to build the luminous system Webb detected. A simple image becomes a compressed record of invisible generations. The dot in the deep field is not first light in the simplest sense. It is light from a place where earlier light had probably already come and gone. The second hidden step is gas supply. A bright early galaxy needs fuel. Stars do not appear because gravity wishes them into existence. They require cold, dense gas. In the early universe, gas flowed along filaments of the cosmic web into growing dark matter halos. These flows could feed young galaxies rapidly. They were not smooth rivers in the ordinary sense. They were gravitational streams, shaped by dark matter, mergers, pressure, shocks, and radiation. If gas arrived too slowly, a galaxy would remain faint. If it arrived too quickly and collapsed efficiently, it could produce intense star formation. JADES-GS Z140 points toward an early environment where fueling worked unusually well. But gas supply also creates danger for the galaxy. Young stars are not gentle. Massive stars flood their surroundings with ultraviolet radiation. They heat gas and can push it outward. Supernovae can drive outflows. Black holes, if present, can inject energy into surrounding material. A small galaxy can lose gas more easily than a massive one. This is the feedback problem. A young galaxy must form stars, but those stars can damage the conditions needed for more star formation. It is like lighting a fire with fuel that blows itself away. For JADES-GS Z140 to become bright so early, feedback could not simply destroy the system. The halo must have held on to enough material, or gas must have kept returning, or star formation must have happened in bursts, timed with the available fuel. That is why one confirmed object can become a test of many ideas at once. The question is not only how far away it is, the question is whether feedback was weaker, gas accretion was stronger, dark matter halos formed earlier, star formation was more efficient, dust behaved differently, or the first stellar populations were more luminous than expected. Each possibility changes a different part of the early universe machine. Some change the stars, some change the dark matter environment. Some change how we translate light into physical properties. The galaxy is a clue, but it does not point to only one solution. The third hidden step is measurement. A galaxy at this distance is not measured the way we measure a nearby galaxy. We cannot send a probe. We cannot resolve individual stars. We cannot watch its spiral arms turn or track its star clusters one by one. We receive a faint signal stretched by cosmic expansion. We use filters, spectra, breaks in light, emission lines, models, and comparisons. That makes the discovery powerful, but it also makes it delicate. The farther we look, the more carefully every interpretation must be built. Redshift is the backbone of the distance claim. Because the universe expands, light from distant galaxies is stretched toward longer wavelengths. A galaxy that emitted ultraviolet light in the early universe can be seen by Webb in infrared today. For JADES, GS Z140, the spectroscopic observations were crucial because photometric candidates can be misleading. A very red object might be extremely distant, or it might be a nearer object with dust or unusual properties. Spectroscopy turns the guess into a stronger measurement. The Lion break, caused by neutral hydrogen absorbing light at certain wavelengths, helps mark the galaxy's extreme redshift. Later observations from ALMA added another kind of confirmation by detecting oxygen emission and refining the redshift. These details matter because the claim only becomes meaningful when the distance is secure. This is one reason the title should feel dramatic, but the script should stay careful. JADES-GS does not break the universe. It does not prove cosmology is wrong overnight. It does not mean the Big Bang did not happen. It does not erase decades of measurement. What it does is force a sharper question about the first few 100 million years. It says that galaxy formation at cosmic dawn may have been faster, brighter, or more efficient than many people expected. That is already dramatic enough. The truth does not need exaggeration. A galaxy seen when the universe was about 2% of its current age, already luminous enough to challenge models, is a strong story without turning it into false science. The oxygen detection makes the story more concrete. Oxygen is familiar because we breathe it, but in astronomy it is also a marker of stellar processing. It tells us that stars have already done chemical work. When ALMA detects an oxygen line from such a distant galaxy, it is not simply adding decoration to the Webb image. It is opening a new window on maturity. A chemically primitive galaxy would be closer to the raw material after the Big Bang. A chemically enriched galaxy has a past. It has previous stellar deaths inside its history. It has a memory written into its gas. That is why the discovery feels like finding footprints in a place where you expected untouched snow. The line also helps astronomers measure distance with greater precision. In a nearby object, a small redshift uncertainty may not change the story much. At redshift 14, precision matters enormously, because a small shift in redshift can correspond to meaningful differences in cosmic age and interpretation. The ALMA result tightened the distance estimate and strengthened confidence that this is truly an object from the extremely early universe. That moves the discussion from whether the object is real to what it means. Once the galaxy is secure, the burden shifts to theory. Models must explain its brightness, its size, its chemical state, and its place in the wider population of early galaxies. Then comes the next question. How many more are out there? One galaxy can be rare. A handful can still be rare. But if Webb and future surveys keep finding luminous galaxies at redshifts above 10, 11, 12, 13, and 14, the population becomes impossible to ignore. The early universe may not have been sparsely lit by a few fragile sparks. It may have contained a surprising number of compact, bright, rapidly forming systems. That would change how we understand the growth of structure. It would affect reionization. It would affect the timeline for chemical enrichment. It would affect how quickly the cosmic web turned dark matter scaffolding into visible galaxies. This is where JADES, GS, Z140 becomes more than a single record holder. Records are useful for attention, but populations are useful for science. The deepest question is not whether one galaxy appeared early. It is whether the early universe was systematically more productive than expected. Were these galaxies forming stars at extreme efficiency? Were their initial mass functions different, meaning they formed a larger proportion of massive stars? Were their dark matter halos more numerous than predicted? Were observations selecting short-lived bright bursts that make galaxies look more massive than they are? Or are our models of early feedback and gas cooling missing something important? Every new confirmed object changes the balance between those answers. A useful way to imagine this is to think of a dark landscape after sunset. If you see one campfire far away, you might say someone arrived early. If you see campfires across the hills, you have to rewrite the story of the whole valley. Webb began revealing more campfires than many expected. JADES-GS Z140 is one of the farthest and most striking, but it sits inside a broader pattern. The early universe may have been busy. It may have produced luminous systems quickly and repeatedly. The problem is no longer a single dot. It is the possibility of an entire dawn that happened faster than our instincts allowed. Reionization adds another layer to the timeline. After the cosmic microwave background formed, the universe entered a long period when neutral hydrogen filled space. Light from the first stars and galaxies began ionizing that hydrogen, carving transparent bubbles into the fog. Eventually, the universe became mostly ionized and transparent to ultraviolet light. Early galaxies are not only objects inside this process, they may be engines of the process. Their radiation helped change the state of intergalactic space. A bright galaxy at redshift 14 raises the question of how much ionizing radiation early systems produced and how much escaped into the universe around them. Escape fraction is one of those technical ideas that becomes dramatic when translated into a scene. Young stars can produce powerful ultraviolet light, but the light must escape its galaxy to affect the wider universe. Gas and dust can trap it. Dense clouds can absorb it. A galaxy may shine brightly to us in some wavelengths, while still keeping much of its ionizing radiation inside. If early galaxies had high escape fractions, they could reionize space more efficiently. If they had low escape fractions, more galaxies or more extreme sources would be needed. JADES-GS Z140 sits at a time when this question becomes urgent. It helps show what kinds of objects existed near the beginning of the process. The galaxy's size also matters. It is not a giant like the Milky Way, but for its time, it is impressive. A spatially resolved galaxy at such a high redshift suggests structure, not just a point-like flash. That matters because some early candidates might be powered by active black holes, which can make compact sources very bright. But if the light is extended and dominated by stellar emission, then stars themselves are doing much of the work. That makes the problem harder in a different way. It means the universe was not merely creating bright black hole beacons. It was assembling stellar systems. It was building galaxies in the real sense. Black holes still remain part of the story. The early universe contains another puzzle. How some supermassive black holes grew so large so quickly. Quasars at high redshift show that enormous black holes existed early as well. If early galaxies and early black holes both grew rapidly, they may be connected by dense environments, efficient gas inflows, and rare halos. But for JADES-GS Z140, the evidence suggests its light cannot simply be explained away as a black hole pretending to be a galaxy. That makes it valuable. It pressures star formation models, rather than letting the mystery escape into an active nucleus. A black hole can be strange. A galaxy full of stars this early may be even more informative. The phrase, "breaks our timeline," should therefore mean something precise. It means the galaxy breaks the comfortable version of the timeline, the one where the cosmic dawn is slow, sparse, and dim. It does not necessarily break the measured age of the universe. It breaks expectations about how quickly visible complexity could appear. It pushes the beginning of organized starlight closer to the Big Bang. It compresses the time between dark matter collapse, star formation, stellar death, chemical enrichment, and galaxy brightness. It makes the first chapters less empty and more crowded with physics. That distinction gives the documentary its spine. We can move through the second half not by repeating that the galaxy is old, but by asking what each part of the discovery demands. What does its brightness demand from stars? What does its oxygen demand from earlier generations? What does its redshift demand from distance measurements? What does its abundance demand from cosmology? What does its existence demand from future telescopes? Each question opens a concrete section. That is how the story stays alive without becoming waffle. The galaxy is not only surprising once, it is surprising in different ways at different levels. The first level is light. The light from JADES-GS Z140 began traveling when the universe was young enough that almost everything familiar did not exist. It crossed space while galaxies merged, while clusters formed, while the Milky Way assembled, while the sun ignited, while Earth cooled, while oceans formed, while life evolved, and while humans learned to polish mirrors and cool detectors in space. The light is not old in a poetic sense only. It is a physical survivor. It moved through an expanding universe for more than 13 billion years and still carried enough information for instruments to decode. A single photon arriving at Webb is a messenger from a galaxy that may have changed beyond recognition long before Earth formed. The second level is time. Seeing JADES-GS Z140 is not seeing where it is now. It is seeing where and what it was. The galaxy we observe is a childhood image of a system whose later history is unknown. It may have merged into larger galaxies. It may be part of a massive structure today. It may no longer exist as a separate object. This is one of the strange emotional truths of astronomy. The farther a discovery is, the less it is an address, and the more it is a memory. JADES GS Z140 is not a place we can visit in the form we see. It is a preserved frame from a vanished era. The third level is ancestry. If a galaxy is already chemically enriched, then it carries the fingerprints of stars that are not visible. Those earlier stars are the missing ancestors. They might have been massive, short-lived, and violent. They may have formed in small halos, exploded, and enriched gas that later flowed into the galaxy we observe. They may have belonged to systems that merged into it. They may have lived and died before JADES-GS became bright enough for Webb. This means the discovery points beyond itself. It is an object at redshift 14 that implies activity at even higher redshifts. It is a window, but it also casts a shadow backward. The fourth level is method. Webb did not simply take a beautiful picture and declare victory. The discovery required careful selection from deep imaging, follow-up spectroscopy, redshift confirmation, physical modeling, and later cross-checks from other facilities. That process matters because the public often sees only the final image. But in early universe science, the path from dot to conclusion is a chain of evidence. Each link must hold. A red color suggests distance. A spectrum tests it. A break in light supports it. A line detection strengthens it. Model fitting estimates physical properties. Other observations refine the story. JADES-GS Z140 is a triumph not only of telescope power, but of verification. The fifth level is humility. Every time astronomy opens a new window, the universe looks less obedient than expected. Hubble revealed deep fields crowded with galaxies. Planck mapped the afterglow of the Big Bang with exquisite detail. Webb looked into cosmic dawn and found bright early systems. Euclid and other surveys are mapping large-scale structure. Each instrument expands the evidence and removes a little more guesswork. But each one also reveals complications. The universe is not designed to match the simple version in our heads. It does not care whether our timeline feels comfortable. It forms structures according to physics, and our task is to catch up. That is why future observations are not a side note. They are the next act. Webb can continue finding and confirming galaxies near the cosmic dawn. ALMA can detect far-infrared and submillimeter lines that reveal gas, dust, and elements. Ground-based extremely large telescopes may eventually help study faint early sources in new ways. Future space missions could map early galaxies across wider areas. Each instrument gives a different piece of the same ancient puzzle. Webb is powerful, but it is not the final eye the human species will build. JADES-GS Z14 may be remembered as a milestone on the path towards seeing even closer to the first stars. One future possibility is that astronomers find galaxies even earlier than JADES-GS Z140. That would not make JADES meaningless. It would make it part of a sequence. The record will move closer to the Big Bang. The known population will grow. The early universe will become less mysterious in some ways and more mysterious in others. New objects may be fainter, smaller, more primitive, or unexpectedly bright again. Some may show fewer signs of chemical enrichment. Others may reveal that star formation was already underway in pockets of the universe at shocking speed. The frontier will not be a single name. It will be a moving edge. Another possibility is that improved models explain JADES-GS Z140 without requiring a radical change to cosmology. Perhaps rare halos, bursty star formation, low dust, and efficient gas inflow can reproduce the observations. Perhaps early galaxies look surprising because our sample was incomplete before Webb. That would still be a major discovery. Science does not become less interesting when a mystery becomes solvable. It becomes more powerful. A solution would tell us which physical ingredients mattered most in the first galaxies. It would show how nature built visible structure, quickly, without needing to rewrite the entire universe. A third possibility is that the population remains difficult. If many confirmed early galaxies are too bright, too massive, too mature, or too chemically enriched for standard models, then theorists may need deeper revisions. Those revisions might involve star formation, feedback, dust, halo growth, black hole contributions, or the statistical properties of early density peaks. They might not overturn the Big Bang, but they could reshape the detailed story of cosmic dawn. That is where the excitement lives. The strongest science often happens between two extremes. Not everything is wrong, but something important is missing. For viewers, the most important thing to understand is that early galaxies are not only distant objects. They are laboratories for physics under conditions we cannot reproduce. The gas was more pristine. The universe was denser. Galaxies were smaller and more chaotic. Mergers happened more frequently. Radiation fields were different. Dark matter halos were just beginning their long assembly into the cosmic web we see today. By studying one galaxy at redshift 14, scientists are not simply cataloging a remote dot. They are testing how matter behaves near the beginning of structure. This makes JADES-GS Z140 different from a spectacular nearby object. A nearby nebula can be beautiful. A nearby galaxy can be rich with detail. But JADES is a clock. It is a measurement of what had already become possible by a particular cosmic age. It tells us that, before the universe reached 300 million years, at least one galaxy was bright, structured, and chemically revealing enough to cross cosmic time and be detected. That sentence carries more weight than the image itself. The image is tiny. The implication is enormous. The next part of the mystery is the first light we still have not seen. Webb can see extremely far, but the true first stars may be beyond direct detection as individual stars. They may have lived in small systems, burned out quickly, and left indirect traces. Their explosions may have enriched gas. Their radiation may have begun ionizing their surroundings. Their remnants may have helped seed black holes. We may never see many of them directly. Instead, we infer them from later objects, like JADES, GS, Z140. The galaxy becomes an archaeological layer. It is not the first artifact in the ground. It is a layer that tells us older layers must exist underneath. That is a powerful way to visualize the early universe. Imagine a desert where the surface looks empty. Then someone finds a ruined wall. The wall is old, but it is not the beginning of the story. Someone had to quarry stone, carry it, shape it, build with it, and live near it. The wall implies a hidden civilization before the visible ruin. JADES works similarly. Its light is ancient, but its chemistry and brightness imply earlier activity. The galaxy is the wall. The first stars are the missing builders. This archaeological view also prevents the story from becoming repetitive. Instead of saying again and again that the galaxy is old, we can ask what evidence is buried inside it. The redshift tells us when the light was emitted. The brightness tells us about stars. The spectrum tells us about distance and gas. Oxygen tells us about earlier stellar generations. Size tells us about structure. Population statistics tell us about how common these systems may be. Future surveys tell us how far the timeline can be pushed. Every measurement becomes a clue in a cosmic excavation. There is also a philosophical, but still concrete point about naming. Catalog names like JADES, GS, Z140 sound cold. They are not designed for emotion. They are coordinates in a scientific archive. But behind that name is a discovery that changes how we imagine the beginning. A name that looks like a machine label points to a place where the first architecture of the universe was already forming. That contrast is part of the beauty. The universe does not label its wonders poetically. Humans do. Science begins with a catalog entry and ends with a changed view of reality. The phrase, "our timeline," should also be understood as human. The universe has no obligation to follow the pace we expected. The timeline that breaks is not time itself. It is our mental schedule. We thought certain things needed longer. Webb shows that some of them may not. We thought the first bright galaxies might be rarer or dimmer. Webb shows that some were bright enough to see. We thought chemical maturity would take more time in the earlier systems. ALMA suggests enrichment could happen very quickly in at least one case. The universe did not rush. It simply followed conditions we are still learning to calculate correctly. This is why JADES, GS, Z140 belongs in a long, calm space documentary. Its drama is not an explosion in the present. Its drama is the slow realization that the beginning was more active than expected. A viewer can fall asleep to the gentle motion of deep field images and still absorb a profound idea. The universe was building complexity before Earth, before the Sun, before almost every galaxy we recognize today. The calm tone does not weaken the story. It makes the scale easier to feel. As the second half moves towards its ending, the question becomes what JADES says about us. It says that human beings are late observers of an ancient process. We arrived long after the first galaxies formed, but we built instruments capable of reading their light. We live on a small planet around an ordinary star, Yet we can measure oxygen in a galaxy from the cosmic dawn. That is not only a scientific achievement, it is a strange connection across time. Atoms made in stars allow minds to study the first systems that made atoms like them possible. There is a loop hidden here. Early stars forged heavy elements. Later generations of stars and planets formed from enriched material. On at least one of those planets, life evolved. Eventually, life built telescopes. Those telescopes detected galaxies where enrichment had already begun. The universe used stars to make the ingredients that would one day allow it to examine its own first lights. JADES, GSZ14. 0 is part of that loop. It is both a subject of observation and a distant ancestor of the conditions that made observation possible. The galaxy also reminds us that cosmic history is not a smooth staircase. It is full of sudden phases, rare peaks, rapid growth, quiet intervals, violent feedback, and hidden transitions. A simple chart can make the universe look orderly. A real observation makes it look alive with exceptions. That is where the best science often begins. An exception appears. Researchers test it. Some explanations fail. Others improve. The timeline becomes richer. JADES may not be the final answer to cosmic dawn. It is a signpost pointing deeper. If future telescopes push earlier, the next frontier may be less visually satisfying, but more important. The first stars may not appear as clear galaxies. They may leave subtle signatures in background radiation, chemical patterns, or faint sources near the edge of detection. The first black holes may reveal themselves through X-rays or infrared light. The first enriched gas may appear through lines detected by instruments that require extraordinary sensitivity. The early universe will not hand over its secrets easily. It has hidden them behind distance, redshift, faintness, absorption, and time. That difficulty is part of the reason JADES, GS, Z14, matters. It proves that the search is not hopeless. Webb did not merely look into darkness and find nothing. It found structure. It found galaxies. It found a record-breaking system bright enough to study. Then other observatories added more information. This is how the frontier moves. Not by one perfect image, but by layered evidence. Every instrument catches a different part of the ancient signal. Together, they turn a faint point into a story. The story also has an important warning. The earliest galaxies can be misused in public discussion. A surprising object can become a claim that all science is collapsing. That is not how real discovery works. When JADES, GS, Z140 challenges models, it is not a disaster for astronomy. It is astronomy doing what it is supposed to do. Models are tested against nature. Nature surprises us. Models improve. The fact that a galaxy can pressure our theories is not a weakness. It is the reason we build telescopes in the first place. The universe is too large, too old, and too detailed to be fully captured by first guesses. Every major instrument has shown that. The first radio telescopes revealed strange sources. X-ray telescopes revealed violent high-energy objects. Hubble deep fields revealed galaxies everywhere. Webb is revealing that the early universe was luminous in ways we did not fully expect. Each step expands the picture. None of it makes the search pointless. It makes the search necessary. So what should the viewer carry from this video? Not that JADES, GS, Z14, magically destroys physics. Not that the universe is suddenly older because one galaxy is bright. Not that every timeline is useless. The real takeaway is sharper. The early universe was capable of building luminous, chemically interesting galaxies extremely quickly. That means the first chapters of cosmic history were more active than they once appeared. Darkness did not last as a simple empty stage. Structure arrived, stars ignited, elements formed, galaxies assembled, and some of that happened early enough for Webb to catch it near the edge of time. That is why the title works. JADES-GS breaks our timeline because it breaks the comfortable human version of cosmic order. It forces us to move earlier, faster, and deeper. It tells us the young universe was not waiting quietly for complexity to begin. It was already building. It was already changing. It was already lighting itself from within. In the final minutes, the script can return to the image itself. A tiny red point in a deep field. Easy to miss. Easy to underestimate. Around it, darkness. In front of it, more than 13 billion years of expanding space. Behind it, unknown generations of the first stars. Inside it, the evidence of record formation. Around it, a universe still emerging from cosmic dawn. That is the power of the image. It does not look dramatic because the drama has been stretched across time. The galaxy's photons are quiet when they arrive. They do not announce that they have crossed almost all of cosmic history. They do not explain that they left when the universe was young. They simply land on a detector, one faint signal among many. Then humans measure them. We compare wavelengths. We calculate redshift. We test models. We argue carefully. We confirm with other instruments. And slowly, a dot becomes a message. The message is not finished. More data may refine the galaxy's properties. More distant galaxies may be found. Some interpretations may change. Better models may remove some tension and reveal new tension elsewhere. That is normal. The frontier is always unstable, but the core lesson will remain. The early universe was not as empty, slow, or simple as it once seemed. JADES GS Z14 is a reminder that looking back in time is not like reading a clean book from page 1. Many pages are missing. Some are burned, some are written in wavelengths our eyes cannot see. Some are hidden behind fog. Webb found one of the early pages, and it was already full of activity. That is the unsettling part. The book had a plot before we expected it to. And perhaps the strangest part is that the discovery makes the beginning feel both closer and farther away. Closer, because we can now see a galaxy from less than 300 million years after the Big Bang. Farther, because that galaxy implies earlier unseen events that still escape direct view. Every answer opens a deeper layer. Every record points beyond itself. Every first light hints at something before it. That is why JADES GS Z14 is not only an ancient galaxy, it is a doorway. On one side is the universe we can measure. Redshift, spectra, oxygen, brightness, size, models. On the other side is the hidden dawn. The first stars, the first enrichment, the first dark matter halos bright enough to become galaxies. We stand at the doorway with a telescope, receiving light that left before the sun existed. And we ask, how much happened before that light began its journey? The answer is not complete yet, but the outline is becoming visible. The universe forms structure quickly. Stars may have lived and died earlier than our old mental pictures allowed. Galaxies may have grown bright in rare, dense regions, while most of the cosmos was still dark. Heavy elements may have appeared in pockets sooner than expected. The first chapters may have been crowded with events that only now are becoming visible. There is another reason the discovery feels strange. The early universe gives astronomers very few clean views. Between us and cosmic dawn, light passes through expanding space, foreground galaxies, intergalactic gas, detector noise, and the limits of every model used to interpret faint sources. A nearby galaxy can be photographed again and again from many angles in many wavelengths. An object, like JADES GS JWST. Zero is more like a whisper at the end of a storm. Scientists have to separate the whisper from everything between here and there. That is why confirmation is so important. It is also why the galaxy becomes stronger as more independent lines of evidence agree. Foreground confusion is one danger. A faint red source could be blended with another object. Light from a nearer galaxy could contaminate a measurement. A dust-reddened galaxy at a lower redshift could mimic the colors of a very distant one. A weak, active galactic nucleus could make a source brighter than expected. Gravitational lensing could magnify a background galaxy and change its apparent brightness. These possibilities do not make the discovery weak. They are exactly the traps astronomers check. The more extreme the claim, the more carefully the alternatives have to be removed. JADES, GSS, Z14. Became important because the evidence survived that process. It was not only a red speck in one image, it became a spectroscopically supported object at the edge of the observable record. Gravitational lensing deserves its own moment because it can make the early universe look deceptively bright. A massive foreground object can bend space enough to magnify something behind it. Some of the most distant galaxy candidates are found with help from lensing clusters, where nature itself turns gravity into a telescope. But lensing can also complicate interpretation. If a galaxy is magnified, it may appear brighter than it truly is. For JADES, GS, Z14. The story is especially interesting because it was found in a deep field, without relying on a massive lensing cluster as the main explanation for its visibility. That makes its brightness harder to dismiss. It suggests the galaxy itself was genuinely luminous for its time, not merely boosted into view by a cosmic magnifying glass. Dust is another hidden variable. In young galaxies, dust is both surprising and important. Dust grains are made from heavy elements, so they cannot exist before stars create the ingredients. But once dust appears, it changes everything. It absorbs ultraviolet light, re-emits energy at longer wavelengths, shields gas, cools clouds, and changes how star formation proceeds. In some models, early galaxies may go through dusty phases that hide much of their star formation, then clear channels through outflows, and become bright in ultraviolet light. A galaxy can therefore look different depending on when we catch it. If JADES, GS, Z14, was observed during a relatively clear and luminous phase, then its brightness may be part of a rapid cycle rather than a permanent state. That does not remove the timeline problem. It refines it. A bursty galaxy still needs the gas, the stars, the enrichment, and the feedback cycle in place early enough to produce the burst. A clear phase still requires dust to form and then be moved or reduced. A temporary bright stage still implies an underlying system capable of dramatic change. In fact, burstiness may make the early universe more interesting. Instead of smooth growth, early galaxies may have flashed, dimmed, cleared themselves, refueled, and flashed again. Webb may be catching some of them during the moments when they become easiest to see. The cosmic dawn may have flickered rather than steadily brightened. Simulations are where these ideas are tested. Astronomers and cosmologists build computer models that follow dark matter, gas, gravity, star formation, stellar feedback, black holes, radiation, and chemical enrichment across cosmic time. These simulations are not perfect copies of the universe. They include approximations because no computer can track every atom in a galaxy over billions of years. But they are powerful laboratories. If a simulation produces galaxies like JADES, GS, Z14 under plausible physics, the mystery becomes more understandable. If it cannot, then some ingredient may be missing or miscalibrated. The galaxy becomes a benchmark, A model of cosmic dawn now has to answer a simple question. Can you make this object on time? Different simulations may answer in different ways. Some may create bright early galaxies by forming stars more efficiently in rare massive halos. Others may use bursty star formation, where short, intense episodes dominate the observed light. Some may require weaker feedback, so gas remains available. Others may point toward unusual stellar populations with strong ultraviolet output. A few may explore whether black hole accretion contributes. None of these answers is as dramatic as saying the universe is broken, but together they show the real depth of the problem. JADES GS Z140 is not a single surprise sitting outside science. It is a test object sitting inside a large network of competing explanations. The cosmic microwave background provides another boundary. It shows us the universe when it was about 380,000 years old, long before galaxies. That map is extremely smooth, but not perfectly smooth. The tiny variations in it are the seeds of later structure. Between that afterglow and JADES GS Z140, the universe had to move from small density ripples to an actual luminous galaxy. That is one of the most dramatic transitions in cosmic history. It is not enough to say a galaxy appears at 290 million years. The deeper question is how those faint ripples grew into a working system so quickly. The CMB gives the initial pattern. JADES gives a later checkpoint. Theory must fill the gap between them. This gap is one of the most mysterious stretches in astronomy. It includes the dark ages, the first stars, the first black holes, the first galaxies, and the beginning of reionization. We have pieces of evidence at both ends, but the middle is still difficult. We know the universe was smooth and hot near the beginning. We know it later contained galaxies, clusters, and heavy elements. The question is how the transition unfolded in detail. JADES GS Z140 sits near the far side of that missing middle. It is early enough to challenge the timeline, but late enough to be visible as a galaxy. That makes it a bridge between what we know and what we still cannot see. There is also the problem of scale. A radius of a few hundred parsecs may sound small beside the Milky Way, but at cosmic dawn, that is not trivial. A compact early galaxy can hold intense star formation in a relatively small volume. Gas densities can be high, stars can form in crowded regions, radiation fields can be fierce, supernovae can overlap, outflows can break through the surrounding gas. If you could somehow stand outside such a young system, it would not look like a calm spiral galaxy. It might look chaotic, blue, irregular, and violent, with bright star-forming regions fighting against the gas that feeds them. The calm red dot in the telescope hides a young engine. The color itself is a trick of cosmic expansion. The galaxy was not necessarily red in its own time. Much of its light began in ultraviolet wavelengths, produced by young, hot stars. As space expanded, that light stretched into infrared before reaching Webb. To our instruments, the distant galaxy appears as a faint infrared source, but in its own era, it was a place of energetic radiation. This is another reason the image can mislead casual viewers. The red dot looks old and cold. The galaxy itself was young and hot. We are not seeing red because the object was gentle. We are seeing red because the universe stretched its light for 13 billion years. That stretch also means the galaxy is part of the story of expansion. Distance in cosmology is not simple. The light travel time, the present distance, the redshift distance, and the appearance of the object are all connected but not identical. JADES GS Z140's light took about 13.4 billion years to reach us, yet the region associated with it is now much farther away because space expanded while the light traveled. This matters for the emotional scale of the video. The galaxy is not merely far in the ordinary sense. It is far inside an expanding history. We are seeing a young object from a region that has moved into a vastly different cosmic context. This is why the viewer should not imagine a telescope simply zooming across a static universe. Webb is not looking through a still room. It is looking down a tunnel of time carved by expansion. Each more distant galaxy is seen at an earlier stage. Eventually, the tunnel reaches the cosmic microwave background, then becomes opaque to ordinary light. JADES GS Z140 is close to the visible frontier where galaxies first become accessible. Beyond it lie earlier sources, fainter objects, and perhaps the first stars themselves. The telescope is not just looking farther, it is trying to catch the universe before it became familiar. The discovery also changes how we think about the Milky Way's own ancestry. Our galaxy did not appear fully formed. It grew through mergers, gas accretion, star formation, and chemical enrichment. The ancient galaxies Webb sees are not necessarily direct ancestors of the Milky Way, but they reveal the kinds of systems that existed when galaxy building began. Some early objects may have merged into larger galaxies. Others may have become the cores or building blocks of later structures. Looking at JADES is not looking at our childhood exactly, but it is looking at the childhood era of galaxies. It helps explain the universe that eventually produced galaxies like ours. There is a second emotional turn here. The atoms in Earth, and in every person watching, come from stellar processing. Heavy elements were built by stars and stellar deaths across cosmic history. Seeing oxygen so early reminds us that enrichment began long before our solar system. The chemistry needed for planets did not begin near the Sun. It began in countless earlier systems, scattered across galaxies that lived and died before Earth existed. JADES GS Z140 shows that this enrichment process was underway near the beginning of visible structure. It turns the early universe from a simple hydrogen and helium story into a place where the periodic table was already beginning to grow. The word oxygen can also be misunderstood. Detecting oxygen in a distant galaxy does not mean there was breathable air, life, or Earth-like conditions. It means ionized oxygen in gas, observed through a spectral line. That distinction is important because it keeps the science clean. The discovery is not about biology. It is about chemical maturity. It shows that stars had already produced heavier elements. That is dramatic enough. In a script, this should be made clear so the title remains exciting without misleading the viewer. Oxygen here is not a sign of forests. It is a sign of stellar history. Another question is how JADES GS Z140 fits with the broader expansion history of the universe. The standard cosmological model includes dark matter, dark energy, ordinary matter, radiation, and the initial conditions seen in the CMB. Early galaxy observations do not usually challenge the whole model directly. They mostly challenge the messy astrophysics of how gas becomes stars inside dark matter halos. This is where public language can become confusing. Cosmology tells us the stage and the clock. Galaxy formation tells us what actors appear on the stage and how fast they move. JADES does not necessarily change the stage. It may change the script of the actors. That difference is subtle, but important. If someone says, "This galaxy is too old, so the universe must be older," they are skipping many steps. The careful version asks whether the galaxy's inferred properties are correct, whether the redshift is secure, whether stellar populations are modeled correctly, whether dust or black holes contribute, whether star formation was bursty, whether dark matter halos were rare but possible, and whether selection effects make bright objects more noticeable. Only after exhausting those details would one look for more radical changes. Real science moves through the careful questions first. That is what makes the story more trustworthy. In a calm documentary, trust matters. Viewers may come for wonder, but they stay when the narration feels grounded. The title can be bold. The explanation should be precise. JADES-GS breaks our timeline because it pressures our expectations, not because it proves every textbook is wrong. That balance is the key. It keeps the video from becoming clickbait, while still giving the viewer a powerful mystery. The universe can be more surprising than our models, without being magical. The best visual structure for this part would be layered. Begin with the red dot in a deep field. Pull back to show the web field. Then shift to a timeline, from the Big Bang to the present. Mark the cosmic microwave background. Mark the dark ages. Mark the first stars. Mark JADES, GS, Z14, at less than 300 million years. Then show hidden processes before it. Dark matter halos, gas collapse, first star explosions, oxygen enrichment, and a young galaxy brightening. This gives the viewer concrete movement, instead of abstract repetition. Each visual answers what had to happen before the dot. Then the documentary can move from the dot to the instruments. Show Webb's segmented mirror. Show NIR cam gathering faint infrared light. Show NIRSpec spreading light into a spectrum. Show armor dishes on the Atacama Plateau detecting a line from cold cosmic gas. The story becomes a chain of machines listening to different pieces of the same ancient object. Webb sees the stretched starlight. ALMA catches a far infrared oxygen signal shifted into millimeter wavelengths. Together, they make the ancient galaxy less ghost-like. They give it distance, chemistry, and physical weight. From there, the visual sequence can enter the galaxy itself, not as a literal photograph, but as an informed reconstruction. A compact young system, dense star-forming regions, hot blue stars, gas clouds, supernova shells, outflows pushing material into surrounding space. No quiet spiral arms, no mature calm disk, no familiar galactic shape. The early galaxy is a workshop. It is building stars, losing gas, gaining gas, enriching itself, and sending radiation into the young universe. This is how to keep the script from drifting into vague awe. The viewer needs machinery. The galaxy must feel active. Finally, the story can point toward the unknown before JADES. The first stars may have been born in mini-halos. The first supernovae may have seeded the gas. The first black hole remnants may have begun growing. The first ionized bubbles may have appeared around clusters of hot stars. Those events are the real hidden prequel. JADES, GS. Z140 is early, but not necessarily first. It is the visible child of even earlier invisible events. That is the strongest ending idea for the second half. The oldest confirmed galaxy is not the beginning, but proof that something even earlier must have been happening. And that may be the real reason JADES-GS feels so powerful. It does not simply show us something far away. It shows us that the beginning was not waiting to become interesting. The universe was already working. Gravity was already gathering. Gas was already cooling. Stars were already changing matter. Light was already preparing a message for a species that would not exist for billions of years. When that message finally arrived, it did not come as a shout. It came as a faint red point in the dark. But inside that point is a challenge to our timeline, a clue to the first galaxies, and a reminder that the universe was building its future almost as soon as it had won.